Michelson's experimental value for the speed of light was 299,920 kilometers per second, or about 300,000 kilometers per second. It was not known whether light travels instantaneously or with finite speed until the late 1600s. Galileo tried to measure the time a light beam takes to travel to a distant mirror, but it was so short he couldn't begin to measure it. Others tried the experiment at longer distances with lanterns. They flashed on and off between distant mountaintops. All they succeeded in doing was measuring their own reaction times. Light travels fast. Olaus Romer. The first demonstration that light travels at a finite speed was supplied by the Danish astronomer Olaus Romer about 1675. Romer carefully measured the periods of Jupiter's moons. The innermost moon, Io, revolves around Jupiter in 42 and a half hours. The Io disappears periodically into Jupiter's shadow, so this period could be measured with great accuracy. Romer found that while Earth was moving away from Jupiter, the periods of Io were all somewhat longer than average. When Earth was moving towards Jupiter, the measured periods were shorter than average. Romer estimated the cumulative discrepancy amounted to about 22 minutes. So as Earth is moving towards Jupiter, he measured a speed. When Earth is moving away from Jupiter in its orbit around the sun, he measures, takes another measurement, sees what the difference is in the two measurements and says, 22 minutes. That's how long it takes for the light to travel. Light coming from Io takes longer to reach Earth at position D, 6 months earlier, than at position A. The extra distance that light travels divided by the extra time it takes, distance divided by time, gives us speed. Christian Huygens correctly interpreted this discrepancy. Io passed into Jupiter's shadow at the predicted time. The light did not arrive until it traveled the extra distance across the diameter of Earth's orbit. This distance is known to be about 300 million kilometers. Using travel time of 1,000 seconds for light to move across Earth's orbit, making the calculations at the speed of light is quite simple. Speed of light was that extra distance traveled divided by that extra time measured, or 300,000 kilometers per second. The speed of light is about 300,000 kilometers per second, or, more simply put, 3 times 10 to the 8th meters per second. Light travels 1,000,000 times faster than sound. The most famous experiment measuring the speed of light was performed by the American physicist Albert Michelson in 1880. Light was directed by a lens to an octagonal mirror. A beam of light was reflected to a stationary mirror on a mountain 35 kilometers away, so about 50 miles away, then reflected back. The distance was known, so Michelson had to find only the time it took to make this round trip. When the mirror was spun, here's your mirror, here's your light source, here's the telescope of the observer. When the mirror was spun, short bursts of light reached the stationary mirror and were reflected back to the spinning octagonal mirror. If the rotating mirror made 1/8 rotation while the light made the trip, the mirror reflected light to the observer. If the mirror was rotated too slowly or too quickly, it would not be in a position to reflect the light. Here's what that looks like. We have the light source again, there's the octagonal mirror, there's the mountain, and the observer. If the light is spinning too slow, then there's this angle, and it's going to miss the mirror. If it's spinning too fast, then it's going to miss the observer. If it's just right, the light will get to the observer. When the light entered the eyepiece, the time for the light to make the trip and the time for the mirror to make 1/8 of a rotation were exactly the same. Michelson divided the 70-kilometer round trip distance, 35 miles there, 35 kilometers there, 35 kilometers back, by this time, and found the speed of light was 299,920 kilometers per second, which is usually rounded to 300,000 kilometers per second, which is the same exact speed Christian Huygens had predicted. Michelson received the 1907 Nobel Prize in Physics for this experiment. The speed of light in a vacuum is a universal constant. When we talk about vacuum, we talk about there being no air, no pressure. Light is so fast that if a beam of light could travel around Earth, it would make 7.5 trips in 1 second. So that means the circumference of the Earth multiplied by 7.5 will give you the distance light would travel in 1 second. This would be a light second. Light takes 8 minutes to travel from the sun to the Earth and 4 years from the nearest star, Alpha Centauri. There's 31.6 million light seconds in a light year. There's 6 trillion miles in a light year. A light year is not a measure of time, but it is a measure of distance. It would take an airliner flying 600 miles per hour 1.141 million years to travel 1 light year. The distance light travels in 1 year is a light year. Think about this. Light entered the eyepiece when Michelson's octagonal mirror made exactly 1/8 of a rotation during the time light traveled to the distant mountain and back. Would light enter the eyepiece if the mirror turned 1/4 of a rotation in this time? Pause it. Think about it. Talk with somebody. Back. Yes, light would enter the eyepiece whenever the octagonal mirror turned in multiples of 1/8 of a rotation. So 1/8, 1/4, 1/2, 1 in the time light made its round trip. So, to summarize again, what was Michelson's experimental value for the speed of light? You should know this by now. Certainly off the top of your head.